I like to thank the organizers for giving me this opportunity to talk here. So I also thank the previous speaker who has already introduced the problem and told some of my introduction parts. So today I will talk about the dynamics of fluctuation correlation in a driven driven classical system. And this work is done with Oritra Kundu and Tonoy Nag. Oritra is postdoc in Luxembourg University, and Tonoy is he is postdoc in Uppsala University. So, so here I will go quickly with this introduction part. So, this driven system is a lot of interest in this recent time because it gives very exotic phases, which does not have a static analog. But the thing is that if you consider a generic many-body system, which is a chaotic, that is, if it has an interacting system, then if there is a periodic drive, then the energy is not conserved and the system will heat up to the infinite temperature state, so which is the featureless state. So now, but it has been seen that it is generally believed that for such type of system, show some pre-thermal behavior before going to the infinite temperature state. That means there you will get a long time, that is the exponentially long time, where the system does not heat up. So, so if you consider some systems like here, actually initially it is observed in quantum systems. So if there are some systems which has a local norm bound, that is the operator is the which has a local norm bound. So like the spin systems or fermionic systems, for such systems there is a rigorous bound for the pre-thermal time scale where omega is the drive of the frequency of the drive. And also this also realized in experiments with like a driven optical lattice with ultra cold bosonic atoms. So now the question is that this such type of systems is applicable for the finite bandwidth systems, and it, of course, because it is the quantum system, so it has also the finite size effects. So here, can we do better for this such system? So here we considered a classical systems, which is the kicked many-body rotor systems, where the first term is the kinetic term, and the second term is the potential term, and kappa is the kick strength as well as the interaction strength. Okay, so the model is first introduced in this paper, and for this type of systems, we have only one dimensionless parameter, that is the k, which is the kappa into tau. So it has been observed that if you calculate the kinetic energy, that is the average kinetic energy, the average over the initial conditions, then this is the picture that the energy. So after a transient regime, there is a long time where the energy does not grow. So we can see the plateau-like structure. And of course, if k increases, that is like this small k means like large frequency, and big K means the small frequency. So if you have the if you drive the system with a large frequency, then it is have a long this pre-thermal state. And this actually this type of this pre-thermalization, we are calling it statistical Fouquet pre-thermalization, because for this case we have not found the rigorous bound, but statistically we can find this time scale for the pre-thermal state and also calculate the temperature. So we can actually can describe the pre-thermal state with a generalized Gibbs ensemble, and from there we can calculate this pre-thermal time scale and the temperature. Okay, so initially what happens that for pre-thermal regime, the rotors does not absorb energy from the drive, but when this when the time gets larger, so what happens the systems, there is a resonance conditions when the consecutive difference between the consecutive rotors becomes the integer multiple of the frequency. So then the rotor takes the energy from the drive and it hits up finally. Okay, so now these quantities are the average quantity what we have calculated. So now the question is that for how whether we can go beyond the average quantity, and from the for this we have calculated this this fluctuation correlation, the correlation of the kinetic energy fluctuation. And already if you consider some isolated static systems, so for such systems there is this is the spatiotemporal correlation. For there is this type of scaling form is found, where for integrable systems gamma is 1, so this is a ballistic motion. For non-integrable systems it shows that gamma less than equal to 1, so it is sometimes it's subdiffusive or diffusive. So now here we can consider the whole dynamic regimes into 3 regimes. Like one is the prethermal region when the system does not absorb energy, and other is the crossover region, and after then the system will heat up when the kinetic energy grows linearly with the time. So here we can see that when we are inside the prethermal region, so if we calculate this quantity, and we can see that this is the fluctuation correlation as a function of x with different time. So we can see that that if we give a fluctuation in the system in this region, then the this fluctuation actually propagates diffusively inside the system. And when the time increases, so it more spreads. And also it follows the sum rule, that is if you calculate the Cxt over summation over x, then that does not depend on time. Okay, and this we can have a good collapse of this curve with this scaling relation. Like if we scale the x-axis and y-axis in that way, then we will get this scaling relation. Okay, so we can see that in the prethermal regime, the fluctuation spreads diffusively. So actually it supports, because it is also seen in the static systems. So in that sense, our prethermal, this type of result supports that our prethermal state is very nearly to static. Okay. So now we can give a simple hydrodynamic picture for this system also. So where this uxt is the local energy fluctuation, and xixt is the noise term. So this is delta correlated, and we can solve this equation, and we can see that what we have find in the numerical result that we can recover here with this simple hydrodynamic picture. And also this we can see that for a region, that is when k equal to 0.15 to 0.25, this diffusion constant does not depend so much on k, and from the this fluctuation dissipation relation we get dc is proportional to b square, and from here, because c is proportional to k square and b is proportional to k, then this d is more or less independent of k, that we find in this case, like numerical results. So now here it is the result in the heating regime. If you consider this heating regime, so here this fluctuation correlation, we can see it shows some delta function peak. So here correlation are frozen both in space and time, and because it is in the heating regime, we can assume these rotors are actually independent. That is, that angles are statistically uncorrelated, and from there we can find also analytically with this approximation the value of this correlation function. And here some interesting thing that but we did not understand much of here. In the crossover regime, we calculate this C that is correlation, and this is actually fitted with this stretched exponential, where this beta is almost independent of k because we have plotted it for 2k values. And here the correlation are frozen in time but not in space. Okay. So here this is the whole picture. That is this is the different dynamic phases of the systems. So and W is the variance of this fluctuation correlation. So here this is the transient region. After this is the prethermal region where the system does not absorb energy. That is, the energy does not grow or heating is exponentially suppressed. There W is grows linearly, and then this crossover region where the in a system starts heat up, where there W is more or less constant, and after in the heating regime we can see that W tends to 0. Okay, so this is the whole picture for our system. And so here we see that the quasi-static nature of the prethermal phase is supported by this fluctuation correlation, and we can give also the hydrodynamic picture of these prethermal phases. And okay, thank you for your attention.
Any questions?
Oh, quadratic Kirchhoff, that we have checked that up to k equal to 1, the system shows some oscillatory type behavior, and after k, it suddenly like there is a jump. So, suddenly jump, but there is no prethermal region. But there is a heating eventually. Eventually heating, yeah.
In the hydrodynamic picture, the white noise or the delta correlated noise, was that a result of a derivation, or is that
no? This is if we have assumed that if it that, then we can explain that our numerical.
Any more questions? So let's thank the speaker.